Hello everyone, I'm Mehdi, and today I'm excited to explore the fascinating topic of crystallographic points, directions, and planes that are essential concepts in materials science. Let's start with point coordinates. When we talk about point coordinates, we are just referring to a specific position within a unit cell lattice. We describe this position using fractions of the unit cell's edge lengths, labeled as A, B, and C. For example, how about the upper corner of the unit cell? First, let's identify the position in the unit cell. The upper corner can be represented by the dimensions A, B, and C. Next, we will write these as fractions of each edge length. This gives us A over A, B over B, and C over C, which simplifies to 1, 1, 1. Finally, we remove the commas, leaving us with the point coordinates for the upper corner as 1, 1, 1. When it comes to crystallographic directions, we use this algorithm to determine direction indices. First, let's identify coordinates. So, determine the coordinates of the vector tail, point 1, and vector head, point 2. So, then calculate difference. Subtract the tail point coordinates from head point coordinates. Then normalize differences. What does this mean? Normalize the coordinate differences in terms of the lattice parameters A, B, and C. Then reduce to smallest integer values. To do that, just convert the normalized values to their smallest integer equivalents. And finally, enclose the indices in square brackets with no commas. So let's clarify by solving this problem. If point 1 is x1 0, y1 0, z1 0, and point 2 is x2 a, y2 0, z2 c half. So after calculation of the difference and normalizing, we will get 1, 0, and 1 half, which can be reduced to 2, 0, and 1. So final indices is 2, 0, 1. Now let's try to solve another problem. If point 1 tail point is A, B over 2, and 0, and head point or point 2 is negative A, B, and C, let's subtract the tail point coordinates from the head point coordinates to get negative 2a, b over 2, and c. Now let's normalize to get negative 2, 1 half, and 1. Multiply by 2 to eliminate the fraction. So we have negative 4, 1, 2. So place in square brackets, no commas, to format direction indices. So we have negative 4, 1, 2, where the overbar represents a negative index. All directions that are crystallography equivalent have the same atomic spacing are indicated by indices in angle brackets. Well, let's explore common crystallographic directions. This slide features a diagram of a simple unit cell illustrating the following crystallographic directions. 1, 1, 1. This direction runs diagonally through the cube, connecting opposite corners. 1, 0, 0. This direction is aligned along the edges of the cube, extending from one face center to the opposite face center. 1, 1, 0. This direction is also diagonal but runs along the face diagonals of the cube, connecting the midpoint of two adjacent edges. Now let's focus on linear density of atoms. Linear density LD is calculated using this formula. LD equals number of atoms centered on direction vector divided by length of that direction vector. So let's solve a problem. Linear density of aluminum in 110 direction. First, in that direction, there are 2 half atoms from the edges. So totally we have 1 full atom. 1 full atom in the center. Totally 1 plus 1. We have 2 atoms centered on that vector. Then the length of the direction vector for 110 is calculated as length equals radical a squared plus a squared equals radical 2a. Given a is 0.405 nanometer, so length is going to be approximately 0.57 nanometer. So linear density is going to be approximately 3.5 atoms per nanometer. Now let's explore crystallographic planes, Miller indices definition. Miller indices are a notation system in crystallography for planes in crystal lattice. They are expressed as HKL and help in identifying the orientation of a plane within a crystal structure. The algorithm for determining the Miller indices is this. 1. Let's establish a new origin. If the plane passes through the selected origin, establish a new origin in another unit cell. Number 2, read intercepts. Identify and read the values of intercepts of the plane with the x, y, and z axis. Designate these intercepts as A, B, and C in terms of the unit cell dimensions lowercase a, b, and c. Then reciprocals. Take the reciprocals of the intersects. So they are going to be 1 over uppercase A, 1 over B, and 1 over C. Then normalize them. Normalize them by multiplying each by their corresponding lattice parameter, lowercase a, b, and c. So h, k, and l is 1 over uppercase A, 1 over B, 1 over C, multiplied by lowercase a, b, c. Then reduce to smallest integers. Reduce the normalized values to the smallest integer values. And finally, enclose the resulting Miller indices in parentheses with no commas. Well, let's solve some problem regarding crystallographic planes. So in this example, no need for relocation of the origin. Then let's identify intercepts. Intercepts of the plane with the axis are A, B, and infinity. So now calculate the reciprocals. It's going to be 1 over A, 1 over B, and 1 over infinity, which is 0. Now normalize the reciprocals. So we will get 1, 1, and 0. So reduction to smallest integers, the values are again 1, 1, 0. So the Miller indices for this plane are 1, 1, 0. This is another example. Again, no need for relocating the origin. Intercepts of the plane with the axis are A over 2, infinite B, and infinite C. So now let's calculate the reciprocals. It's going to be 2 over A, 0, and 0. By normalizing them, we will get 2, 0, 0. no need for reduction, and the Miller indices for this plane are 2, 0, 0. Let's explore another example. Again, no need for relocating the origin. Intercepts of the plane with the axis are a over 2, b 3c over 4. So, after calculating the reciprocals, we have 2 over a, 1 over b, and 4 over 3c. By normalizing them, we will get 2, 1, 4 over 3. So, how about a reduction to smallest integer? The values are going to be 6, 3, and 4 after multiplying by 3. So, the Miller indices for this plane are 6, 3, and 4. So, the family of planes includes all planes that are crystallographically equivalent, indicated by indices in braces. Well, let's explore common crystallographic planes. So, imagine a 3D diagram to help picture these planes. 0, 0, 1 plane. This plane intersects the z-axis and stays parallel to the x and y axis. Think of it as a flat sheet slicing through the z-axis. 1, 1, 0 plane. Here the plane intersects both the x and y axis but stays parallel to the z-axis, forming a vertical slice along x and y. And 1, 1, 1 plane. This one intersects all three axes x, y, and z at equal distances, giving a diagonal slice through the whole unit cell. Well, for hexagonal unit cells, the process is quite similar to the cubic system, but with a few adjustments. First, determine where the plane intercepts the A1, A2, and C axis. These intercepts give you the necessary information to proceed. After finding the intercepts, we express the plane's position using the Miller-Brevis indices H, K, I, and L. These indices are unique to the hexagonal system and describe the plane's orientation. How to find the I index? The I index is derived using the relationship between H and K. In this system, I equals minus H plus K. This ensures that the three indices H, K, and I are related in a way that keeps the symmetry of the hexagonal structure intact. Well, let's focus on planar density of the atoms. So, planar density or PD is calculated using this equation. Number of atoms centered on a plane divided by area of that plane. So, let's explore more by solving this problem. Planar density of 100 plane of BCC iron. So, you see there are 4 quarter atoms. Totally, we have 1 atom centered on that plane. How about the relationship between A and R? When it comes to BCC structure, you know A equals 4R divided by radical 3. So given that R equals 0.1241 for iron, so A is going to be 0.287 nanometer. So PD equals the number of atoms is 1 divided by the area, and the area is going to be A squared. So PD approximately is 12 atoms per nanometer squared. Okay, in this slide we are going to talk about X-ray diffraction. Let's break it down together. X-ray diffraction is a method used to study the structure of materials. When we talk about diffraction of light, there is a key point. For light to be diffracted, the spacing of the diffraction grating needs to be comparable to the wavelength of the light. It means that if the light is too big or too small, it won't be able to diffract properly. Now, how does X-ray work? When X-rays hit a material, they are diffracted by the planes of atoms within it. In other words, atoms act like a wall with specific spacings, and when X-rays hit these walls, they change direction. Finally, let's discuss interplanar spacing. This is the distance between two parallel planes of atoms in a material. This spacing is crucial for analyzing and understanding the structure of materials, helping us learn how they are constructed and what physical properties they have. So, X-ray diffraction allows us to gain important insights into the atomic structure of materials, providing valuable information about their properties. Well, let's now focus on how we can use X-rays to figure out the crystal structure of materials. When X-rays hit a crystal, they interact with the crystallographic planes in the material. Think of these planes as layers of atoms stacked on top of each other. When the incoming X-rays strike these layers, they get diffracted or bent. Now, for us to detect this diffraction, something important must happen. The reflections of the waves must be in phase. It means that the waves should align perfectly with each other at the detector to create a clear signal. If they are not in phase, the signal will be weak or non-existent. So, to understand this better, let's look at the extra distance traveled by one of the waves, which we will call wave 2. The extra distance is given by the formula 2d sine theta, where d is the distance between the crystallographic planes and theta is the angle of diffraction. Now, when we measure the diffraction angle, we can compute the interplanar spacing d using Bragg's law, which is expressed as n lambda equals 2d sine theta. Here, n is the order of reflection and lambda is the wavelength of the X-rays. Diffraction happens when the angle theta equals the angle theta c. Finally, we can measure the intensity of the X-ray reflections using a detector. The intensity helps us understand how many X-rays are being diffracted, which in turn gives us clues about the arrangement of atoms in the crystal structure. So, by analyzing how X-rays diffract off of crystallographic planes and measuring the angles involved, we can reveal the hidden structure of materials at the atomic level. Well, let's take a look at the X-ray diffraction patterns for polycrystalline alpha iron, which has a body-centered cubic BCC structure. In this pattern, you can see distinct peaks that correspond to different crystallographic planes. Each peak represents the diffraction of X-rays by a specific set of planes in the crystal structure. 110 plane. This peak is associated with the 110 crystallographic plane. The intensity and position of this peak provide information about the arrangement of atoms within that plane. Next, we have the peak of 200 plane. Similar to the previous peak, its intensity and location are essential for understanding how atoms are packed in this direction. Finally, we see the peak corresponding to the 211 plane. Each of these peaks gives us insights into the crystal structure of alpha iron and helps us determine interplanar spacing and other structural characteristics. By analyzing the positions and intensities of these peaks, In the diffraction pattern, we can deduce important information about the material's crystal structure and how the atoms are organized. This technique is fundamental in material science and helps to understand the properties of various metals, alloys, and other type of materials. Right. If you found this video helpful, don't forget to like, share, and subscribe for more on material science and engineering. You know, your support means a lot and helps me bring you more of this exciting content. Catch you in the next one.